In the history of human engineering, few inventions have shaped the destiny of nations, the borders of maps, and the course of civilization quite like the cartridge. It is a small, unassuming object, often no larger than a human finger, yet it contains within it the power to project force faster than the speed of sound. To hold a bullet is to hold a masterpiece of physics, chemistry, and metallurgy. But have you ever stopped to consider the immense industrial complexity required to manufacture one? A single round of ammunition is not one piece. It is a system of 4 distinct components working in perfect harmony: the projectile, the case, the propellant, and the primer. If any one of these components fails by a fraction of a millimeter or a milligram, the result is catastrophic. Today, we journey deep inside a massive high-security ammunition plant to witness the creation of millions of rounds of small arms ammunition. This is a world of molten lead, rolling brass, toxic chemistry, and laser precision. Our journey begins not with the explosion, but with the raw earth. The heart of the bullet, the projectile itself, starts as a gray, heavy, and toxic metal, lead. We enter the core foundry, a cavernous section of the factory where the air is thick with heat and the hum of induction furnaces. Here, massive ingots of pure lead, each weighing thousands of pounds, are stacked like bricks. Lead is the material of choice for ballistics not by accident, but by the laws of physics. It has a high specific gravity and density, allowing it to carry momentum over long distances and resist the drag of air resistance. While modern environmental concerns have introduced copper and bismuth alternatives, lead remains the king of ballistics for its ability to deform upon impact, transferring maximum energy to the target. The lead ingots are fed into massive melting pots. These furnaces heat the metal to 621 degrees Fahrenheit, the precise melting point of lead. Inside the cauldron, the gray blocks collapse into a shimmering silver pool of death. Impurities, known as dross, float to the surface and are skimmed off by robotic arms or workers in heavy protective gear. This liquid lead is not cast into bullet shapes immediately. Instead, it is extruded. The molten metal is cooled slightly until it reaches a semi-solid clay-like state. Giant hydraulic presses then force this soft lead through a die, a steel plate with a specific hole diameter. The lead is squeezed out like toothpaste, forming a continuous thick wire that is wound onto massive spools. Each spool holds enough wire to make tens of thousands of bullet cores. These spools are transported to the heading floor. Here, rows of high-speed heading machines devour the lead wire. The machine cuts the wire into precise lengths, known as slugs. The tolerance here is measured in grains, a unit of mass where 7,000 grains equal 1 pound. If a slug is even a grain too light, the bullet's trajectory will be unstable. The machine then hammers the slug into the aerodynamic shape of the bullet core, a boat-tail rear for stability and a pointed ogive nose for cutting through the air. But lead is soft. If fired alone at supersonic speeds, the friction of the gun barrel would strip the lead apart and the heat would melt it. To survive the journey down the barrel, the lead needs a suit of armor. This is the jacket. In a separate part of the factory, immense coils of copper alloy strip are being unrolled. Copper is used because it is harder than lead, but softer than the steel of the gun barrel, allowing it to grip the rifling grooves without destroying the weapon. Giant punch presses stamp out small discs from the copper sheet. These discs look like coins. They are then drawn, stretched out into cup shapes. This is a multi-stage process. You cannot stretch metal instantly. It tears. So the cups are drawn, annealed, heated to soften, and drawn again until they form a perfect thin-walled jacket. Now the marriage of the two metals occurs. In the assembly press, the lead core is dropped into the copper jacket, then a punch descends with tons of force. This process, called swaging, physically bonds the lead to the copper, ensuring they don't separate in flight. The nose of the bullet is formed. For military rounds, it is fully encased, full metal jacket, to ensure penetration. For hunting or self-defense, the tip may be left open, hollow point, to encourage expansion. The finished projectiles cascade out of the machine like a waterfall of shiny copper rain. They are tumbled in polishers with corncob media to remove any manufacturing oil, emerging bright and lethal. But the projectile is useless without a launch vehicle. This brings us to the most complex component to manufacture, the brass case. The casing is the miracle of the modern firearm. It serves as a container, a weatherproof seal, and a gasket that expands to seal the gun's chamber during the explosion. It starts life as a mixture of 70% copper and 30% zinc, an alloy known as cartridge brass. This specific ratio provides the perfect balance of strength and elasticity. The process begins with a cup. Imagine a thick brass coin. This cup is fed into a massive transfer press. The press uses a series of steel punches and dies to stretch the brass. This is deep drawing. The first punch turns the coin into a short cup. The next punch stretches it longer and thinner. But metal has a memory. As you work it, the crystal structure becomes stressed and brittle, a phenomenon called work hardening. If you tried to stretch it further, it would crack. To solve this, the brass must be relaxed. The semi-formed cases are marched through a long oven known as an annealing furnace. Gas flames lick at the brass, heating it to a cherry red glow of about 1,100 degrees Fahrenheit. This heat resets the crystalline structure of the metal, making it soft and malleable again. The cases are then pickled in acid to remove the oxidation scale and washed. This cycle, draw, anneal, wash, draw, anneal, wash, is repeated multiple times. It is a slow, methodical elongation. A short, fat cup becomes a long, slender tube. Finally, the features of the case are machined. The head is formed. This involves flattening the bottom of the case and stamping the rim, which allows the gun's extractor claw to grab the empty shell and throw it out after firing. A tiny hole, the flash hole, is punched in the exact center of the primer pocket. This hole is the gateway for the fire. The manufacturer's stamp, indicating the caliber, like 5.56 millimeters or 308, and the year of manufacture, is pressed into the base with tons of force. The final step for the case is the most critical, the neck anneal. You may have noticed on military ammunition that the top part of the brass looks discolored, showing a bluish-purple rainbow hue. This is not a defect, it is a sign of quality. The neck of the case, where it holds the bullet, must be softer than the base. When the gunpowder explodes, creating 60,000 pounds per square inch of pressure, the neck must expand instantly to seal the chamber and prevent hot gas from blowing back into the shooter's face. But the base must remain hard to prevent the case from rupturing. By heating only the neck with induction coils or gas jets, the factory creates a case with dual properties, soft at the top, hard at the bottom. The cases are electronically inspected by cameras and lasers looking for split necks, dented mouths, or blocked flash holes. Any defect is ejected into the scrap bin. The perfect cases are polished one last time, gleaming like gold, ready for the explosive heart that will give them life.
We leave the deafening noise of the metal presses and enter a restricted, climate-controlled zone. The signs on the blast-proof doors read "Explosives Area." No static, no sparks. This is where chemistry takes over from metallurgy. A bullet is a kinetic energy delivery system, but the energy comes from chemical potential stored in two substances, the primer and the propellant. First, the primer. This is the spark plug of the round. It is a tiny metal cup, no larger than a baby's fingernail, pressed into the bottom of the brass case. But inside this cup lies a microscopic amount of a highly volatile, impact-sensitive chemical mixture. Historically, this was mercury fulminate, but modern factories use lead styphenate or non-toxic diazodinitrophenol, DDNP. Manufacturing this primer mix is the most dangerous job in the plant. It is often done by robots in isolated bunkers or by highly skilled workers behind thick safety glass, working with wet paste to reduce the risk of detonation. The wet primer mix is rubbed into the tiny cups. Once it dries, it becomes incredibly sensitive. The impact of a firing pin, a force of just a few pounds, is enough to detonate it. When struck, the primer explodes, sending a jet of superheated flame through the flash hole and into the main body of the case. This flame is what ignites the gunpowder. The primers are pressed gently into the brass cases. Sensors check the seating depth to the thousandth of an inch. A high primer could cause a slam fire, where the gun goes off just by closing the bolt, a catastrophic failure. Next comes the propellant, gunpowder. But powder is a misnomer. Modern smokeless propellant is not a dust, it is precision-engineered extruded grains. It is based on nitrocellulose, derived from cotton or wood pulp treated with nitric acid, and often nitroglycerin. This is double-base powder. The geometry of the powder grain is pure rocket science. The grains can be shaped like flakes, balls, or tiny cylinders, extruded powder. The shape determines the burn rate. Imagine lighting a pile of sawdust versus a pile of wood chips. They burn at different speeds. In a pistol, the barrel is short, so you need a fast-burning powder, flakes, that releases all its energy in a millisecond before the bullet leaves the barrel. In a sniper rifle, the barrel is long. You need a slow-burning powder, cylinders, that continues to push and accelerate the bullet all the way down the barrel. The factory uses automated hoppers to dispense the powder. The accuracy is critical. Powder is measured in grains. The variance allowed is often plus or minus 0.1 grain. If a machine drops too little powder, you get a squib load. The bullet gets stuck halfway down the barrel. If the shooter fires again, the gun explodes. If the machine drops too much powder, the chamber pressure spikes, destroying the weapon and injuring the user. Laser sensors verify the powder level in every single case before it moves to the next station. Now the grand convergence, the loading machine. This is a rotary turret that moves with blinding speed. The primed, powder-filled case arrives at the seating station. The copper-jacketed bullet is dropped into the mouth of the case. A seating die descends, pressing the bullet down to a specific depth known as the cartridge overall length, COAL. This length is vital. If the bullet is seated too deep, it compresses the powder, causing pressure to skyrocket. If it is too long, it won't fit in the magazine or the chamber. Finally, the crimp. The machine squeezes the neck of the brass case tightly against the bullet. This holds the projectile firmly in place, ensuring it doesn't get pushed back into the case during the violent recoil of an automatic weapon. The finished rounds are ejected from the machine, a cascading river of gold and copper ammunition. They are tumbled once more to remove grease and then undergo a final visual inspection. But looking good isn't enough. They have to perform. We move to the ballistics laboratory. This is an indoor underground tunnel equipped with the most advanced measurement instruments money can buy. It smells of burned powder and ozone. Technicians randomly select rounds from each lot for destructive testing. The ammunition is loaded into test barrels, heavy universal receivers clamped into massive steel vices. These are not regular guns, they are laboratory instruments with pressure sensors drilled into the chamber. The trigger is pulled. Crack! The sound is deafening. As the bullet leaves the barrel, it passes through chronographs, optical screens that measure velocity. A standard 5.56mm NATO round must travel at approximately 3,000 feet per second. That is nearly 3 times the speed of sound. If the velocity is too low, the batch is rejected. If it's too high, it's dangerous. Simultaneously, a piezoelectric transducer measures the chamber pressure. The graph on the computer screen spikes to 55,000 or 60,000 psi in microseconds. The pressure curve must be smooth and consistent. They also test for accuracy. At the end of the 100-yard tunnel, the bullets hit a target. The group size, the spread of the bullet holes, is measured. For match-grade ammunition, the spread must be smaller than a dime. High-speed cameras, recording at 100,000 frames per second, capture the bullet in flight. They check for yaw. Is the bullet wobbling? Is it spinning perfectly? A bullet spins at over 200,000 RPM due to the rifling. This gyroscopic stability is what keeps it point forward. For military contracts, the testing is even more rigorous. They test terminal ballistics, what the bullet does when it hits a target. Blocks of ballistic gelatin calibrated to mimic the density of human muscle tissue are fired upon. High-speed video analyzes the wound channel. Does the bullet fragment? Does it penetrate deep enough? Does it expand? They also conduct environmental torture tests. The ammunition is frozen to -40 degrees and heated to 140 degrees to ensure it fires in the Arctic tundra and the desert sands. They soak it in salt water and tumble it in vibration machines to simulate being carried in a soldier's pack for months. Only after passing this gauntlet of physics and chemistry is the ammunition approved for packaging. It is loaded into trays, boxed and wrapped in plastic. Pallets of ammo weighing tons are loaded onto trucks. From the raw mines of lead and copper to the high-tech sensors of the ballistics lab, the creation of a bullet is a sobering reminder of human ingenuity. We have mastered the elements of the earth to create small, precise packets of energy that have defined the modern world. Whether used for sport, defense, or war, the manufacturing of ammunition is an industrial ballet of fire, metal, and math executed millions of times a day with zero margin for error.